Hi, this video is an introduction to the different types of metamorphic rock that you can come across in your A-level geology exams. Much like the metamorphic rocks you can see here exposed in the walls of the Black Canyon of the Gunnison in Colorado in the USA. There are two groups we can put metamorphic rocks into, depending on how they form. Regional metamorphic rocks will show some kind of foliation. This is where we get an alignment of crystals within the metamorphic rock. These crystals will grow perpendicular to the stress or the pressure that's applied to those rocks. It should be quite a distinctive feature of these rocks. Now, examples of these will include slate. Now, this is a rock formed by the compression of mudstone. It forms at moderately high pressures, but really quite low temperatures, which is why it looks so similar to mudstone. We don't get a lot of recrystallization in this rock. What we do see, though, are platy minerals like the clay, any chlorite or biotite mica that might be in there, will get aligned. Again, at right angles to the direction of stress. The foliation in this rock is called a cleavage. It's not always easy to see in a thin section, but if you look carefully on this slide, you can see there is that preferred orientation, that alignment of crystals. All of which, of course, forms at right angles to the principal stress directions. Occasionally, we will see some remnants of the bedding from the original mudstone preserved in the slate. It's what we call a relic structure. The relationship between the cleavage, shown in green, and the bedding, shown in blue, can indicate the way up of the slate that we find it in. This tends to happen, though, at a lower metamorphic grade. Higher metamorphic grades will destroy any evidence of this bedding. If we have higher pressures and higher temperatures, we'll start to see more recrystallization of the original minerals from the parent rock. With a mudstone, this means that a slate at higher temperatures and higher pressures will transform into a schist. Now, a schist is defined by its schistose texture. This is where we have crystals of mica growing along the foliations. That's really what defines this rock as a schist. This particular one has porphyroblasts, or new larger crystals that have grown within the rock during metamorphism, of garnet. This indicates a higher temperature of formation. This creates a very, very distinctive texture in a thin section. You can see we've got beautiful euhedral porphyroblasts of garnet here, and you can see very clearly the foliation within the mica. You can see also how that mica has been distorted by the growth of the porphyroblast within the rock. Remember, this all happens during solid state recrystallization. And again, this schistose texture forms at right angles to the principal. The highest grade regional metamorphic rock is gneiss. This forms at very high temperatures and very high pressures. But it doesn't form as a result of melting. This, really, as far as we're concerned, is pretty much the last stage of metamorphism before melting would begin. What we see in this rock are bands of different coloured minerals. The lighter coloured minerals, things like quartz, orthoclase feldspar, will band together. The darker ferromagnesium minerals will also band together. And we get a very distinctive, almost striped appearance to this rock. Again, this can be down to the recrystallization of mudstone. And again, this foliation will form at right angles to the principal stress. Contact metamorphism also shows recrystallization of rocks, but what we don't see here is the foliation. These rocks tend to form at much lower pressures, so we don't get an alignment of the minerals. We can get this spotted rock where we get new minerals starting to grow within a metamorphic rock. In this case, these spots of new minerals are actually concentrated along old laminations, which could be slightly confusing to make you think it might be a foliation. You always need to look at the context of this rock. Where does it actually come from? Perhaps a more common type of spotted rock we might see is this Chiastolite hornfels. This is a baked mudstone where new crystals of a distinctive metamorphic mineral called Chiastolite have formed. It's very characteristic stuff, forming needle-shaped crystals with a distinctive square cross-section. If we have limestone as our parent rock material, we can see a marble will form. This is recrystallized limestone, made of calcite, but has a very distinctive, saccharoidal is the fancy name for it, but it's really a sugary texture. Of course, it's very recognizable by dropping some acid on this. If we look at it in a thin section, we'll see possibly a Nulitic limestone there with a distinctive round ooids, turning into this crystalline structure of marble. You can, if you look carefully, spot the 120-degree angles between crystal faces on that marble thin section, which is very, very distinctive of these fused, recrystallized grains within a contact metamorphosed rock. Sandstone can give us a similar looking rock when it's metamorphosed. This creates a rock we call a metaquartzite. Superficially, it can look similar, but clearly this rock is going to be predominantly quartz. So if you test the minerals, you'll be able to recognize the difference. You can see the texture of a metaquartzite can look very similar to that of a marble. So, to conclude, the type of metamorphic rock is linked very much to two factors. Firstly, the parent rock material. What do you start with? And secondly, the grade, the conditions of metamorphism that are applied to that rock. Those two factors combine to create the range of metamorphic rocks that we see for our A-level. Now remember to come up with your interesting question and bring it along to class. I'll see you then.